In the last class, we discussed on phenomenal algebras. The video is there, you can watch. Today, we will discuss about representations of sister algebras. Okay, so we want to discuss about representations. We have already discussed representations of C of x, the sister algebra C of x. And we indeed know that any representation is just a star homomorphism. It fits pi of x star, pi of x star is pi of x star, and pi of xy is pi of x times pi of y. It's just a unital representation, is just a unital star homomorphism between C of x and between the C-star algebra to some B of h. Bounded operators and algebra. We know all representation of C of x. It will indeed look like pi is up to unitary equivalence, it will look like some pi mu is for some measure, some mu k or something, and this tensor some k power n, the same thing. I mean, not tens, I mean, no, it is repeated, right? The direction, it's repeated k times, some kn, and then direction over kn, k equal to 1 to infinity. Other things may be different representation, equivalent representation. So this is how it will look. We have used Zorn's lemma to prove it. The same thing is true, and this pi mu k are basically first we proved that anything can be written as a direction of cyclic representation. So these are cyclic. In the case of C of x, we know any cyclic representation is given by a measure, 1L2 mu. So in the general statement is, I mean, what is it? The cyclic representation? Pi is cyclic if there exists a xi in H such that you take pi of x xi, where x in the C-star algebra A, and then you take the closure in the Hilbert space, and that should be H. This is what the definition of cyclic is. So the same proof works here. I will just orally say what the proof is. Pi is any representation, A is any C-star algebra. Pi is any representation where we assume our Hilbert space to be separable and all that. Then there exists, then it is countable union or countable direct sum of cyclic representations. Okay? Where it may repeat, and then I mean it's countable direct sum cyclic representation. The same proof, given any vector xi, I mean, you consider the sub-representation. Sub-representations are given by invariant subspaces. You take a subspace, x of h naught is contained in h naught in H. Then you can restrict that to here. And the orthogonal complement will also restrict because pi of x star will leave that invariant, and it's closed. Orthogonal complement will also get restricted. So if you take any single vector, you can apply pi of x, any vector, then you take the closure, you take the span and closure, that will give you H naught. So there are sub-representation, maybe its whole thing, that's different, but there are sub-representation, and you take orthogonal collection of such sub-representation, which are cyclic, and there will exist a maximal element. If you apply the Zorn's lemma in a natural way, there will be a maximal element. And that maximal element, the direction should be equal to H. Otherwise, it will not be maximal, and the same proof works. The same thing we have already done for C of x, and the same proof works here. So we have to concentrate on cyclic representation. So for C of x, any cyclic representation, yes, said something wrong. Okay. Any cyclic representation looks like is given by a pi mu, from C of x to B of L2x mu. The Hilbert space is L2x mu. You have any cyclic representation is given by a measure on x. So then you form the L2x mu and you take the multiplication representation. F acting on G equal to Fg. Okay, where F is in C of X and G is in L2. Okay. So there is a natural way of what is called quantization or quantizing any objects. See, the C of X is a commutative element, commutative object. Okay, then you quantize it. What is you mean by quantize it? You make it non-commutative. That is what is a sister algebra A is. That's one way of doing it. I mean, there are. See, the thing is, if you have in a quantum world, you don't have points. I mean, if you learned some quantum mechanics, no, in the first year, second year, you don't have it. Oh, you don't have your computer. Second year or second year physics they have. Okay, so there is no fixed point. There is no fixed position for a particle, quantum particle. There will be only probabilities for it to exist in different places. So this is like a sample space where you have a probability or something. But then you can't talk the usual classical probability to do that. I don't know whether I mean, whenever I talk last year when I gave the quantum probability course, I talked about this in the first class. So you cannot use a sample space, or you don't have a set to work with to where a particle is something. So for that you have to what is called you have to deal with. So instead of set, you deal with functions. It's also same thing. See, for example, if you have L infinity, all the indicator set functions are there. So it is like the sets are there already. So quantizing means you take a non-commutative sister algebra. See, if you have a C of X, for example, if you have just n points, finite number of points, for example. If you have some finite set, 1 up to n, okay, then you want to talk about, so there are n possibilities for some particle or whatever, some event, something. The events are subsets of this, okay. So then what will you do? So if you will consider functions from this set, okay, this is some x, your x, okay, some x to c. You want to consider functions like this. These functions you can actually represent it as a representation. You can represent it as diagonal elements of a matrix. So it will act on Cn. These are functions acting on C. So functions, the elements, I mean, sets are this. For any set, you can consider a corresponding, I mean, set can be indicator function on that set. You take that set and it takes the value 1 in that set. So sets can be embedded here. So points can be embedded here. And then for any function, you can have it as diagonal matrix. So this is commutative. You allow in a non-commutative things, and the events will correspond to projection. That is some sort of non-commutative analog of the classical objects. Okay, that is what is considered in the quantum setup. Okay, so we have to consider the non-commutative analog of this L2. Non-commutative analog of L2 is the Hilbert space. Non-commutative analog of C of X is the A. The one thing is the non-commutative analog of the integration. I mean, it will be more simple here. The thing is, integration is just a linear function. It is just a linear function, integral. So if you have in C of X to C, it is just a linear function. F going to integral F d mu. So this is the linear function. So non-commutative integration, I mean, the integration is a linear function of C of X. So that gives you, I mean, when you have a measure, you have an integration. So using this integration, you define this L2. Okay. So instead, you can have non-commutative. I mean, you for a general C-star algebra, you just have to consider linear functional. But any linear functional may not give it because you have this positive measure. Okay, you are using the positive measure for some reason. So for that, what you need is what is called a positive linear functional. So you have a measure, you get a representation here. You have a measure on C of X, you get a representation. So measure corresponds to a positive linear functional on C of X. So we will consider positive linear functionals on a C-star algebra, and using that we will construct a representation similar to this, very similar to this. Okay? That is our plan. So definition, you can see that integration will satisfy this condition. A be a C-star algebra, and phi from A to C, okay, a linear functional. I'm not saying it's bounded now, it will automatically bounded. You don't need that condition. Is a linear functional. Is positive, is said to be positive if P of x is greater than 0, if x is greater than 0. I mean, we have the notion of positivity for elements in system algebra. So if x is greater than 0, this is a number, complex number. This has to be, this is equivalent to saying P of x star x is greater than or equal to 0 for all x. Okay, this is the definition of positive linear function. Okay, so this is like integration. I mean, any positive linear function you can call that it is analog of integration. Okay, in fact, any positive linear functional on C of x will be given by a measure, and that is indeed corresponds to integration, right? That's what Riesz representation theorem says. Any positive linear functional is given by a measure. So this is exactly the analog of integration here. This positive linear functional. So if you have a positive linear functional, then if you have two elements x, y, and a, okay, and phi is a positive linear functional, okay, so C phi is greater than a positive linear functional, then we can define some sort of something like this, okay, which is equal to phi of y star x. Okay. Then this is linear in the first variable. You just define something like some function like this, two variable function like this, which is equal to phi of y star y. Linear in the first variable because x is here. Conjugate linear in the second variable. Okay. And it is in fact phi of x will be phi of x star x is positive. Okay. And x is positive, which is phi of x star x is positive. So this is the semi-inner product. Strictly positiveness may not be given. I mean, phi of x, xx, the inner product xx equal to 0 need not imply x equal to 0. That we have to do something. But it's a semi-inner product. And semi-inner product will satisfy Cauchy-Schwarz inequality. Okay. So this will satisfy Cauchy-Schwarz inequality. Then using the semi-inner product, we should get an inner product and construct a space. And that is what our new L2 non-commutative L2 will be. And here exactly like left multiplication, it will act as a left multiplication. That is our construction. Okay. So I want to make a following proposition. I mean, this is which says that any positive linear function is actually continuous. Phi from the following are equivalent. The two conditions are equivalent. One, phi from A to C is positive. The positive linear function, okay, which is equivalent to saying phi is actually bounded and phi of 1 equal to norm phi. Okay. So a positive linear functional, if you have a positive linear functional, then it is automatically bounded and it satisfies condition. Conversely, if a bounded linear functional satisfies just this condition, the norm is attained at 1. 1 is the identity element in system algebra. So norm is attained at 1, then it is positive. Okay, that's what this proposition says. So proof. So phi is a positive functional, positive linear functional. We want to prove phi is bounded and phi of 1 is 1. So if you have a positive linear functional, maybe I put a phi here, if you, okay, so that this is, I mean, I put a phi here. Okay. This is linear, I mean, this is depending on phi, this is the semi-inner product. Okay. We know that is a semi-inner product. So, okay, let's assume phi from A to C is positive. It's a positive linear. Okay. Then we want to prove phi is bounded and phi of 1 is equal to norm phi. That's what we want to prove. Okay. So we know that, so if x is self-adjoint, then x can be written as x equal to x plus minus x minus, where both x plus and x minus greater than or equal to 0. This is clear, no? Because any x is, I mean, any x is given by some f of x. I mean, either by self-adjoint, we know functional calculus. Okay, any function, any real x is self-adjoint means that that function, the corresponding, I mean, f of t equal to t, that function in the c of x, that is c of sigma x, that's a positive, that's a real value function. The sigma is real. Okay, so you can take the negative part and positive part of the function. If you have any function, that can be written as f plus minus f minus, any function. You take the corresponding positive function, will give rise to positive elements in the C-star algebra. So this is clear. Okay. So anything can be written like this. So in particular, phi of x will be phi of x plus minus phi of x. Thus, this will be real. The x is self-adjoint, then phi of x is real. Okay. And also phi of x bar equal to phi of x star is equal to phi of x bar. These are some properties. I mean, I should have said it earlier, but anyway, this thing should come here. Okay. After discussing positive linear functional, I should have said. If you have a positive linear functional, then phi acting on a self-adjoint element is real, and phi of x star, any element, I mean, this is for all x. I mean, this is for all x. Phi of x star equal to phi of x is not for self-adjoint, they're same. Phi of x is real if it is self-adjoint, but any element in C-star algebra can be written as some x1 plus I y1, where x1 and y1 are self-adjoint. And phi of x1, and because it's linear, it will be just bar of that, right? Phi of x star equal to phi of x bar. This is some x1 plus I y1 means this will be x1 minus I y1. So phi of x star equal to phi of x bar. So any positive linear function will satisfy this condition. We further have that is a semi-inner product, so that will satisfy the Cauchy-Schwarz inequality. Okay. Cauchy-Schwarz inequality. So let me write the Cauchy-Schwarz inequality for xy in A. The Cauchy-Schwarz inequality says that the inner mod of the inner product is less than the norm of the individual things. So which is same as saying xy, the norm square is less than or equal to norm p square, norm. I mean, this is not correct. This is not, I mean, this is not norm, this is not inner product. These are all just semi-inner product. So I will write the condition. Okay. So, I mean, semi-inner product will give rise to semi-norm, and it will satisfy the Cauchy-Schwarz inequality. Okay. So what we have is xy, which is equal to phi of y star x mod of this is less than or equal to phi of x star x power half, phi of y star y power half. So since I am taking power, I put a square here. This is true. So this is Cauchy-Schwarz inequality. Okay. If I apply Cauchy-Schwarz inequality to that semi-inner product, you get this. Okay. Now you take y equal to 1. Okay. Y is the identity. Then this implies phi of x square. So mod phi of x square is less than or equal to phi of x star x times phi of 1. Okay. Because this is, I mean, if you have a positive linear functional, it takes positive elements to positive elements. So if we have a partial order, not partial order, x is greater than or equal to, we make sense out of that. So we see that x star norm x square times 1. Okay. This is, I mean, norm x square times 1 minus x star x is greater than or equal to 0. Say it again. This is for all x. This is for self-adjoint. This is true. Maybe you take it y. Okay. If phi of x is in R, if x is self-adjoint, okay, this is a separate statement, I said. So when it is for a general x, this is true. This is a pure. That's because any element can be decomposed as x1 plus iy1, where x1 plus iux2, where x1 x2 are self-adjoint. Because of that, you apply to that, you get it. So this is true as operators. I mean, as elements of C-star algebra. Why is this? You just apply this, no? Norm x square, xi, this norm x square minus x star x, xi. Wait. No, this is not C-star algebra. This is not operators, no? So, I mean, this has, why is this true? X star x is, x star x, norm of x star x is less than or equal to norm x square. Norm of x star x equal to, you have to prove that the spectrum is contained in the positive real line. Okay, and spectrum of this will be, you have sigma x star x, that will be contained in the sigma of x star x. It's contained in 0 norm x square, right? I mean, spectral radius is, this is positive, so spectrum has to be in the positive real line, and its spectral radius is norm x star x. So it will be here like this. Okay, and so sigma of x star x is contained in this. So by yeah, this is positive. So for any positive element, the spectrum is contained in positive approved. For a general C-star algebra, any positive, I think we proved, no? Any positive element has positive spectrum. We did for BH. We didn't prove that. For any positive element, the spectrum is positive. Yeah, we did for BFH, right? Yeah. You have to, we didn't prove. So we'll prove it after this. Okay, assume it for some time. So I'll come to that. Yeah. For a general C-star algebra, yeah. Okay. So is there any other way of doing it? I'm just wondering. Let's not. Yeah, we can't avoid that. Yeah. Okay, then it follows from the polynomial spectral mapping theorem, right? This is just, I mean, then for any constant, I mean, this is just a constant. This is just a polynomial in x star x, right? So this implies sigma of norm x square 1 minus sigma of x star x is contained in that. That says that, I mean, this is contained in 0 infinity, right? That's right, no? Yeah. Okay. Yeah, I have to prove that if x is greater than 0, then sigma x is contained in the positive region. I have to prove that. Okay, I'll come back to that. Yeah. It's you'll prove it. So I will prove it after this. Okay. Okay. So once we have it, then this is true. So phi of norm x square times 1 is greater than or equal to phi of x star x. Okay. Because it's positive linear functional. So we have that phi of x mod f square is less than or equal to phi of x star is less than the so norm x square times. I mean, this is, you have phi of 1 you will get, right? This is norm x square, you can take it out and you will get phi of 1. So phi of 1 square. So this implies norm of phi is less than or equal to phi of 1. That's what this inequality says. But a phi of 1 is 1. So it has to be phi of 1. I mean, norm is attained at phi of 1. So this says norm phi is less than or equal to phi of 1. Norm of 1 is 1 in this is algebra. That is clear. That we haven't proved, but it's clear. The phi of 1 is a self-adjoint element and the spectrum is just 1. So it's clear. Okay. Spectral radius is 1. Okay. So norm phi equal to phi of 1. So this way is proved. One way, 1 implies 2 is proved. Okay, 2 implies 1. So we have a bounded linear functional and it attains its norm at 1. Then we have to prove it's a positive linear function. Okay. So positive linear function means you have a x greater than or equal to 0. You want for x greater than or equal to 0, you want phi of x greater than or equal to 0. Okay. So that is if its spectrum is contained in, again, I'm assuming that fact. If the spectrum is contained in 0 infinity, then I have to prove it. So it is enough to prove if sigma x is contained in some interval AB for a self-adjoint element, x is self-adjoint. Okay. Sigma x is contained in the interval AB, then we proved that phi of x is contained in, we will not get AB, we will get some phi of 1 times AB. Okay. If phi of 1 is a positive number, because phi of 1 is equal to norm phi, I mean, we assumed phi of 1 is equal to norm phi, so phi of x is contained in this. This is what we will prove. It's enough to prove this. Okay, then sigma x is contained in 0 infinity, then phi of x will be a positive number, right? That's what we want. Okay, when this follows. From this it will follow. So sigma x is contained in AB. I mean, let's assume that AB looks like C minus R, C plus R, C minus epsilon or C plus whatever. Okay. Then we have x minus C times 1, okay, is contained in minus RR. Okay. So in particular, norm of x minus C times 1 is less than or equal to R. Okay, this is self-adjoint. Okay, so this is true. Okay, now phi of x minus C mod of this is less than or equal to norm of x minus C times x minus C times 1. By C, I mean C times 1. C times 1 times norm of phi. This says that phi of x minus C times phi of 1 mod of this is less than or this is equal to phi of 1, right? Norm phi equal to phi of 1. Phi of times x minus C. This is less than or equal to R. We have assumed that that is less than or equal to R. Okay. So this implies phi of x is in phi of 1 times C minus C plus R. That's good. Okay. Phi of x C times phi of 1 is phi of 1. I mean, there's a phi of 1 common. So that's what we want to prove. Okay. 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 Suppose, so we want to discuss cyclic representation of Hissisar algebra. So suppose a representation is cyclic. suppose pi from a C-star algebra to B of H is cyclic, that is, there exists a vector xi in H such that pi of x xi I thought there is uninterrupted supply. No, only internet is not there. Zoom, camera, everything is working. Those. No, even internet is there. Why the Zoom has gone? Okay. So, yeah. So if we have any cyclic representation of some A on P of H, we want to prove that every C-star algebra admits a representation, isometric representation of P of H. So you don't need to talk about C-star algebra as an abstract object. You can as well consider it as something contained in P of H. That is one thing. And another thing is, if you want to consider different representation, different embedding of a C-star algebra need not have one way of embedding. It may be different. You can consider as different acting on different Hilbert spaces. Okay, so different realization. C-star algebra is an abstract object, but it may have different realization. Okay, unless they are all isomorphic, there is no point in talking about that, right? So, so, so that is what we want to prove. Okay, whatever the theorem we are going to prove is basically says that everything can be realized as operators. Okay? So if you have a cyclic representation, that is, it has a cyclic vector. Okay, so now this closure in the inner product is H. Then we can define a phi corresponding to this phi as P of x is equal to pi of x xi xi. Okay. And if xi is a unit vector, also we assume that xi is a unit vector, which you can assume if you want, you can divide it. So then this is actually a positive linear function. If you take pi phi of x star x, this is then pi of x star x, which is pi of x star pi of x. Okay. And this is a positive linear function greater than or equal to 0. And it's a unital and all that. I mean, pi of 1. If this is unital, that okay. So this is indeed a positive linear function. Okay. So given a cyclic representation, you get a positive linear functional like this. So given a positive linear functional, you want to construct a representation so that this relation is satisfied for that between the representation and the positive linear functional. That is what is called GNS representation, what I am going to talk about. Okay. The definition is a positive linear function. We want to consider something like analog of probability measures. Okay, positive linear functions are analog of positive measures. So this is analog of positive linear positive probability measure. So a positive linear functional is said to be a state if its norm is 1, phi of 1 equal to 1. Its norm is phi of 1, and that is equal to 1. Its norm is 1. See, if we have a measure, complex measure, then there is it's a set of all complex measure on C of x forms a Banach space, and its norm is the total variation measure we talked about. So in particular, for a positive measure, there is no separate total variation measure. It's just mu of x, okay, mu of the whole set. So if that is 1, that is the state. I mean, that corresponds to it's a probability measure if the mu of the whole set is 1. So that corresponds to the norm of that is 1, which is equivalent to saying phi of 1 is 1. Okay. We actually want to say norm of phi is 1. Okay. I don't know whether the spelling is correct. This is what is called GNS representation. So like P from A to C is a state. It's a positive linear functional with norm 1. Then there exists a Hilbert space P and as xi phi in H phi into 1 and the representation phi of B of H phi such that phi of x you will get it that way. Yeah. So we have already done part of it. Given a positive linear functional, we get a semi-inner product. We want to quotient its kernel and then get a inner product. And on that, we will define the same way we did for measure C of x as multiplication operators. And we just want to verify everything, whether everything goes through. That's what we want to do. Okay. So define. Maybe I'll put it because I want this is not the inner product. So I will just write like this xy for the time being equal to phi of y star x. It's a semi-inner product. Okay. Then this satisfies the Cauchy-Schwarz inequality, which says that phi of y star x is square is less than or equal to phi of x star x. Okay. Now you define n phi equal to all such x in A such that phi of x star x equals 0. Okay. Then if x is in n phi is equal to saying phi of x star x is equal to 0, which is equivalent to saying phi of y star x equals 0 for all y. Of course, if you take x, phi of x star x is also 0. So this is true. Okay. So this clearly implies that n phi is algebra. No, it's not algebra, it's a vector space. Okay. N phi is clearly a vector space. And also n phi is more than that, it's a left ideal. I mean, it's algebra also. If you put an xy, that's also satisfied, right? Yeah. We just want to quotient it as a quotient it. I mean, we want to get a Hilbert space only. Okay. The n phi is a left ideal. We need left ideal because we want to multiply through left. Okay. That should be well defined. For that, we need the left ideal. Okay. So this is a left ideal. That is clear if x is in n phi, then yx is in n phi for all y, right? That's clear. Oh, sorry. So n phi is a left ideal. So we defined a semi-inner product and we define this n phi, which is where it's zero space, and it's clear, we see that it's a left ideal. Okay. Then you take H to be, HP to be A, not HP, HP not, put a not top on it. Okay. Not to be A quotiented with NC. That is all those things which looks like this. Okay. Where if X minus Y is here, I mean, it's in. Okay. Quotient space. Now you define X plus NP, Y plus NP equal to P of X star, Y star X is an inner product. Of course, the only condition is the strictly positivity. Okay. If you take P of X plus NP, X plus NP, then P of X star X, which is greater than or equal to 0. Okay. And that is equal to 0, X will be in NP. And NP is a 0 here, right? In the quotient space, NP is a 0. Okay. I mean, if this X plus NP, X plus NP equals 0, implies P of X star X equals 0, implies X is in NP. Okay. So this is the inner product on the quotient space. So when you have inner product on some space, you can complete it. The inner product will extend to a genuine inner product on that, then be Hilbert space. Okay. You must have seen it in the first course in function analysis. Okay. Now HP equal to HP naught, the completion with respect to this inner product. Okay. You can complete any metric space. The same thing will work here. Okay. So you take the completion, and this inner product, because of the continuity of the inner product, it will give rise to an inner product on the completion. So now the HP is a Hilbert space. Okay. Okay. Now you define for so I want to define X in A. I define, so I will first define it on that. This is a dense subspace. HP naught is a dense subspace of HP. Okay. So I define LX from HP naught to HP naught by left multiplication. Because X times NP is inside NP, because it's a left ideal, this is okay. This is well defined. Okay. Because NP is a left ideal. Okay. Now the claim is LX is bounded. LX is bounded on this HP naught. Okay. So if it is bounded on HP naught, you can extend it to a whole of XP. Okay. So it's bounded on HP naught. So we want to show that it's actually norm is less than or equal to norm X. Okay, that's what we want to show. Okay. So norm of LX Y in phi. I mean, the inner product is given by phi. If you want, I can put a phi here. Okay. If you want. Okay. So the inner product is given by, this is equal to X plus L, X, I mean, Y plus, this is XY plus this. So the whole thing is XY times this. So it should be Y star X, Y, right? This is what the norm of this. So enough to prove phi of Y star X, Y is less than or equal to norm of this. This is the, I mean, norm square of this. That's not norm of this. This is norm square of this. This is less than or equal to norm X square, X star X is norm X square, right? This is enough to prove that this is less than or equal to norm of X star X. No, this is LX acting on Y, right? So this is less than or equal to phi of norm phi of y star. One is phi of y star y, that will be the norm. Lx is what is acting. So we get yeah. Yeah, phi of y star y, which is the norm of that, right? We want to prove that this is enough to prove this is less than or equal to norm x square times norm of this y square, right? To prove that this is bounded, Lx is bounded, the norm of Lx is less than or equal to norm x. To prove that, it is enough to prove this. Okay, Lx times y square is less than or equal to norm x square times norm y square. This will imply that norm of Lx is less than or equal to norm x. Right? This is what it proves. But the norm should be in phi norm. This is Hilbert space norm we are taking. Okay. So to prove that, I just write it. This is Lxy is just x times y inside that Hilbert space. X times y plus n phi. And norm Hilbert space norm of that is phi of y star x phi. I mean, it's just the norm of xy times xy star, which is this. Right. Phi of, I mean, norm of x plus n phi is nothing but phi of x star x power half, right? So I've just written the square of that. Is it okay? I mean, I'm saying that I want to prove Lx is bounded. So I have to prove Lx times y is less than or equal to some constant times norm y. Sorry, maybe there is a confusion. Okay, I'll write it again. Lx is bounded on that. So we want to prove Lx acting on y plus np. Okay. Norm of this square is less than or equal to enough to prove NF is bounded. So it's enough to prove this is less than or equal to norm of x star x, which is some constant, okay, which is equal to norm x square. So which is equal to norm x square, okay, times norm of y plus np square. Okay, it's enough to prove this. Okay, is okay. This is just the phi norm, right? It's enough to prove this. So, but this is exactly equal to phi of y star. This is just phi, I mean, Lx of this is xy, right? Which is equal to y star xy. Okay. So, enough to prove phi of y star xy is equal to, but norm of, now this is equal to norm of x star x, right? Okay. Times phi of y star y. Okay. It's enough to prove this for all y. Okay. Now consider another xi of x equal to phi of y star xy. Consider this. Okay. This is a positive linear function. This is linear, of course. Xi of x. If you have a lambda, you can take it out. It's x plus y, you can take it out. I just xi of x, I mean, this is equal to, I mean, I'm just defining it like this. This is positive. If you have an x star x, you will get an x star x, which is in the, I mean, which is like some z star z, that will be greater than or equal to 0. So this is a positive linear function. Xi is a positive linear function. Okay, by the lemma, we have proved norm of xi equal to xi of 1, which is equal to xi of 1 is phi of y star y. Okay. I'm defining a new linear functional like this. That is positive linear functional by the definition. Okay, that's clear. I mean, if you take positive linear functional, xi of x star x should be greater than or equal to 0. Xi of x star x is, you will get an x star x here, which is just xy star xy, which is greater than or equal to 0. Okay. So from the earlier lemma, its norm is attained at 1. Okay. This is not a state. I mean, this is only a positive linear function. So we get this. Okay. Huh? we use it later. I mean, it is just, I mean, because the vector psi b will be 1 and all that. Here we don't need, I mean, it's for the other condition, it is just a technicality, that's all. There is no need. Any positive linear functional, you will get a representation. Okay. We want to get, I mean, any measure, you get a representation of C of x. For probability measure, you have some condition, that's all. Okay, so that implies xi of x star x mod of this is less than or equal to norm x star x times norm xi. But that is equal to norm of x star x, norm x square times phi of y star y. Okay, so that claim is proved. Can you actually see from here? Okay. Okay, that's what we want to prove. We want to prove this. So that is clear. So Lx is bounded on HV naught. So Lx extends to a bounded operator on HV. Okay. Notice Lxy equal to Lx times Ly, which is just left multiplication. This is satisfied on the dense subspace HV naught, and it will be satisfied on HV also. Similarly, addition and all that. So except the star, this is Lx x going to. So I mean, Lx extends to a bounded operator to XP. Call that as pi phi of x. Okay. Now Lxy looks like this. So pi phi of pi phi is a representation, not star. I mean, star we have to verify, except that everything else is satisfied because Lx will satisfy those conditions. And on a dense subspace, so the extension will also satisfy those relations. Okay. Pi phi of xy is pi phi of x times pi phi of y, everything. So we want to verify that it's, and it's critical. Pi phi of 1 is identity on that. Multiplication by identity is just identity. Okay, okay, everything is satisfied. So okay, now we want to verify, need to verify this. Need to verify pi phi of x whole star is pi phi of x star. That's what you want to verify. And it's enough to verify, enough to prove L of x star is L of x star, of course. So to verify that, okay, we verify it on this dense subspace, L of whatever, pi phi of x acting on y plus np from z plus np. Okay, take the inner product, which is equal to it is just phi of xy will be there. So z star xy, which is equal to phi of x star z star y, okay, which is equal to y plus np, the inner product, with x star z plus np, okay, which is equal to y plus np into pi phi of x star times z plus n. Okay. So this implies, I mean, this relation is satisfied in a dense subspace, so it is satisfied everywhere. Phi phi of x star equal to phi phi of x star. Phi phi of x as an operator star, it comes as x star here. So phi phi of x star. So it's a star representation. So phi phi from A to HP star representation, star homomorphism. So as I forgot to say it in the theorem, there is some uniqueness statement. Okay, so further in the statement of the theorem, further, if phi from A to some B of H, I mean the theorem, whatever I have stated is over. This is just some missed out part of the theorem. B of H be any other representation, if is any other cyclic representation, okay, with a cyclic vector xi in H, cyclic vector, okay, with phi of x xi equal to phi of x. Okay. If you have any other cyclic representation which evaluates the state phi of x, we started from a state and we construct a representation. Suppose if there is another representation which is also cyclic and it evaluates the state like this, okay, then there exists a unitary from H to H phi such that u of xi equal to xi phi, whatever the xi, I forgot what is xi phi. Okay, in the earlier theorem, xi phi is just 1 plus np. Okay, then this is clear. If you apply phi of x here, then clearly phi of x, phi phi of x, xi phi. If you take the closure, that is just going to be HP, right? You get all of them. If you apply x here, you get all of A plus np is dense there. You take the closure, it's there. Okay. So the constant function 1 is, I mean, the equivalence class, of course, equivalence class corresponding to the constant function 1 is a cyclic vector. Okay. And u phi of x u star equal to phi of x. Okay. They are unitarily equivalent also. So you just have you have got another representation. So you just have to define the unitary. So define u of, as it's clearly it's written, u of xi equal to xi phi, and u of phi of x xi phi xi equal to pi phi x xi phi. Okay. Then, I mean, you don't need to verify well-definedness. I said that if you can define if you have some set contained in one Hilbert space, okay, and some other set contained in another Hilbert space, you define a function from, just a function from S to S prime, okay? You define a function and verify that preserves the inner product. Then it will be automatically linear, and it will preserve, I mean, it will preserve the inner product to the span of that. So it will extend to the whole of thing. So it will extend to an isometry. And if that function is on to, then it will extend to and if this S prime is also total here, I mean, it's dense here. Sorry, if S is total, S prime is total. If span closure is everything, span closure is everything, then you can get a unitary between them, which we have already used it also, and a question was asked in the exam also. Okay. So then we know that pi of x, xi pi of y, xi equal to pi of x star, pi of y star x, xi, which is equal to phi of y star x, which is equal to, again, same thing. pi phi of x, xi phi, pi phi of the same y z. Okay. So the inner product is preserved. So this map will extend to a unitary, and you can verify, you write it down and you check that that satisfies this relation. Okay. It's an exercise. You just verify that. Okay. So these two representations are unitarily equivalent. So a cyclic representation given by a phi is unique up to unitary equivalence. Okay. This representation is, see, a state is called faithful. Faithful if phi of x star x greater than or equal to 0 implies phi of x equal, sorry, x equal to 0 implies x equal to 0. Okay. And a representation is faithful if phi of x star x faithful means it's, I mean, it's injective. Pi of x, it's enough to prove this. Pi of x equal to 0 implies x equal to 0. I mean, this is injective. So if you have a state is faithful, then the representation will be faithful. You have that n phi, you have defined it. You have that, I mean, there is no kernel for phi. This n phi is 0. N phi is all those x such that phi of x star x is 0. The n phi is 0. Okay. And you can see that it's faithful, but we don't, but even when the state is not faithful, the pi can be faithful. That is possible. But we want to get an injective, we want to get an isometric representation through something else. We want to do the following. So this is the proposition. X is in A, okay, and X is self-adjoint. Then there exists a state phi on A such that phi of x equal to norm x. Okay. You have a state phi of x equal to norm x. So that will imply that I mean, that will imply that pi of x as norm as pi of s as norm. So that, I mean, this will imply that there exists a representation, I mean, the corresponding representation pi phi x norm of this equal to norm x. This is equal to phi of x star x. This is phi of x square, right? I mean, okay. Okay. Pi phi of x is this. So, I mean, once we have this, then it will follow. This will follow. Okay. So we have to get that proof. So X is self-adjoint. Oh, no, we will not do this because this needs girlfriend name theory. So we will not. I mean, this is a general no. I didn't have it in mind. So this will not work. I mean, we proved if you have a self-adjoint element of B of H, then this is algebra generated by this isomorphic to C of sigma of X. We haven't proved it for a general A. So this will not work. This will work for, I mean, if, yeah, we will not do this. Say it again. Norm X equal to no. This is the norm phi of X star. I mean, this is only X square. Norm X square equal to norm X square. Anyway, we will not do this. So, I mean, once you get this, you can take a countable direct sum and you get a this just says that there is an isometric representation for any C star algebra. That's what you want to say. But we need Gelfand-Neymark theory. Let's see whether we want to do it. If I do it in the next week, then we will do it again, or we will not do this. Okay? But anyway, you know how to represent that. If you have a faithful state, then you get a faithful isometric representation anyway.